to the last day of the EC3, and here is Kok-Yiu Xiaowen. And today I will present a topic of enhancing the Visual-LLM through the prompt engineering and Retrieval-Augmented Generation for site safety compliance checking. And as you all know, the construction safety is a global crisis, and in 2022, about 23% of the fatal accidents happened in the construction sectors in Europe, and similar situation happened in both USA or China all around the world. Well, currently there have several limitations regarding the traditional computer vision models. For example, in the first one, as you can see that in the traditional model, each task requires a separate training, and they are basically non-scalable and task-specific models and lack of scalability. And the second thing is that the safety rules are not embedded into the AI reasoning. For example, this one, the rules require to be transferred into the way that a CIB model can understand in case by case and require a high-intensive human effort, and instead of the automatic parsing. And worstly, they are unable to interpret complex relationships. For example, this one, the worker are not facing to the working platform. This kind of spatial relationship is quite difficult for the traditional CV model to understand. Well, the Visual-LLM offers a new hope. It's pre-trained on the word knowledge and can interactively respond to users' ad hoc questions and allow a more flexible way to inject document knowledge. But the key question is that how can VLM have the domain-specific knowledge regarding the construction safety management? Well, there are basically two ways, like in implicit way and the explicit way. For the implicit way, we can do fine-tuning, but the fine-tuning of the LLM is still facing several challenges. For example, there will be inflexibility to the new rules, which are not being pre-trained in the pre-trained data, and it cannot provide that code number for the regulation, and it has the limited context window, which could restrict the capability to inject the various domain knowledge. Well, for the explicit method, we can do prompt engineering. As we can see that for the prompt engineering, directly including those rules into the prompt could improve the stability of the existing fine-tuned model and also enables the charging of the new rules to enable the scalability. So we need to find a way to optimize the potential of the prompt engineering and also to enable the dynamic update of the knowledge injected to the VLM. So our method is hybrid RAG, provides the possibility. It's used off-the-shelf retriever and the in-context learning ability of the LLMs and incorporates the word knowledge into the fixed LLM through the in-context learning window. So in phase one, the VLM will convert the site image to the text feature. And secondly, we will use the hybrid retrieval matches the feature to regulation trunks. And thirdly, the VLM will perform compliance checking, and this leverages LLM in-context learning without fine-tuning. Well, the very first step is to transfer the image to text representation. And we developed a three-phase prompt engineering strategy, and this is based on the human recognition process. In phase one, we require VLM to conduct a global scan to capture all the overall layout of the site. And in phase two, we get the VLM deep into the major activity and object detection. And in phase three, we focus on the very detailed analysis, like the interaction between the workers and also the equipment in the construction site. And this structured prompt output enables a foundation for the precise retrieval of regulation. And here you can see that the comparison between the traditional typical prompt and our prompt strategy result. Our result can analyze the image layer by layer and enable a more accurate identification regarding on the critical details. For example, here you can identify the key elements of that a floor appears to be wet, which is very essential to conducting the welding activity. In the construction safety issues, and each detail can decide everything. And then we need to separate the entire regulation code into smaller chunks, and trunking optimization is very critical. The larger chunks will cause redundancy, while the small chunks will lose the context. So in our papers, we have split regulations according to the structure of each regulation document, according to its structure in an automatic manner. And then we need to embed those trunks into the vector database to store them. We need to first convert these regulation trunks into n-dimensional vectors using the embedding models. And crucially, we inject the metadata, for example, the chapter title, source code into each trunks to enable the traceability and the dynamic update ability. And why hybrid? For the sparse retrieval, it can compensate for the dense retrieval's weakness in the exactly match. For example, for PPE, such kind of keyword, and also for the BS standard, such kind of code. And for the dense retrieval, can handle the semantic links. For example, the head protection and will link to the safety helmet. And which the sparse retrieval cannot do that. So our hybrid retrieval combines the both strengths from these two methods and can achieve higher accuracy. So here we use a re-ranker model to adopt to do the fine-grained similarity comparison. It adopts a cross-encoder architecture and compared with the dual encoder that the embedding model adopts. The re-ranker model allows for full interaction among the query and also the document to reduce the information loss. And to validate our framework, we conduct experiments based on 98 rules from the Hong Kong 2 regulation books and of 115 real construction site image. And we use ChromaDB, BCE embeddings, BM25, and BCE re-rankers as our tools, and we examine our accuracy of the for our entire system. And here you can see the results. Actually, the hybrid retrieval achieved around 78% of accuracy, and the application study proves that all the three components are very critical. If we do not include the sparse retrieval in this hybrid retrieval mechanism, the accuracy will drop about 24%. So the BM25 is essential for extract the code and also the abbreviations. Well, for the dense retrieval, the accuracy, if we don't have them, the accuracy will drop about 9%. So it is vital for the linking concepts such as the head protection gear and all the safety helmet. And also, if we do not have the re-ranking model, the cross accuracy will drop about 24%. So this one the cross encoder will surpass in noise. For example, the irrelevant rules in the welding rules in the construction in the confined space query. Well, here you can see that another finding is that the irrelevant rules may include the hallucination of the VLM. For example, you can see in the left-hand side case one, we have 6 correct rules retrieved from the database. Well, it will lead to the VLM accuracy only achieve 60%. Well, in case 2, we have about 8 rules correct. Well, the VLM can judge them all correctly. And we also quantify them. Like this figure reveals the critical correlation between the correct judgment and also the correct retrieval rules. We can observe that the density peak at the top right. So it's improved that more relevant rule we have, the complex accuracy will improve. This is because the access of the irrelevant roots may influence the VLM's judgment. So to conclude our work, we have demonstrated the potential of enhancing the Visual-LLM through the prompt engineering and also the Retrieval-Augmented Generation for the safety complex checking. And our proposed method effectively addresses the limitation of the traditional CV model to improve the scalability and also the flexibility for the consensus site various purpose. Well, for the limitation and future work, we plan to optimize the roboticness through the dynamic feature fusion and the adverse testing. We also explore the lightweight deployment like the edge computing. And finally, we aim to integrate our framework with the Beam platform to enable its practical value. And that's all for today's my sharing, and thank you all, and welcome any questions. Thank you.
Thank you very much.